Okay, welcome to this lecture for exercise physiology. Today we are going to do a recap on homeostasis. So when we're talking about homeostasis, what are we referring to? Well, the strict definition of homeostasis is a tendency for the body to resist change in order to maintain a constant internal environment. Not unlike we see in the picture there are many systems that our body wants to keep in check, wants to keep things balanced. We have set limits for where we like things to, where our body likes things to be, and our body will work hard to maintain that. So for things like heart rate, breathing rate, body temperature, blood sugar levels, your blood pressure, they are all supposed to be within certain normal ranges, and your body will work to maintain those ranges. There's another very similar term that we're going to use a lot during this module, which is the term steady state. And that's often used to describe a steady and unchanging level of some physiological variable, like heart rate. So your heart rate can be in steady state. There's a key difference, a subtle difference between homeostasis though and steady state. Homeostasis generally is used to illustrate relatively constant and normal internal conditions during resting conditions, whereas steady state doesn't mean it refers to a physiological variable that is constant and unchanging, but not necessarily at resting levels. So we can have steady state at rest, which is homeostasis, but we can also have steady state at other intensities or during other activities as well. So when you are not completely at rest, say if you are sitting upright at your desk, you're quite close to rest, but you're certainly not at rest. But there's loads of variables, all those variables in your body might be steady and unchanging. If you went for a walk, everything might be slightly elevated, but again will be steady and unchanging. If you went for a jog, again they'll be elevated further. Your heart rate, your breathing rate might change, but they can operate at a steady state while you are at that different intensity. Obviously, if we keep pushing things on, there'll be a point where you can no longer maintain steady state during exercise. That's when things start to get a bit challenging. So if we look at the next slide here, we see an example of homeostasis versus steady state using your core body temperature. Your body temperature likes to be controlled around about 37 degrees, but temperature can fluctuate. If you are hypothermic, that is when your temperature has gone a bit low. Hypo is the prefix meaning low. Or if you're hyperthermic, your temperature has gone a little bit too high. Hyper is the prefix meaning too high. In the example you can see on the slide there, we've got someone who's exercising over 60 minutes at submaximal exercise intensity in a thermoneutral environment. So there's a low temperature and low humidity, meaning that they're not building up or accumulating a lot of heat in the body. And what we see there, the body starts off at 37 degrees, which is the resting level, homeostasis. And as the exercise duration progresses, the body temperature rises a couple of degrees, 1 degree, and then at 38 degrees and after around 40 minutes, it levels off at the new steady state level. So we've got homeostasis would be the resting baseline level, body temperature of 37 degrees. During submaximal exercise, in this example here, we've a new steady state level, which is 38 degrees, 1 degree higher. So the plateau in the body temperature there represents steady state because the temperature is constant, it's not changing. However, because it's above the normal resting body temperature, it does not represent a true homeostatic condition. So, therefore, when we use the term homeostasis, it's generally reserved for describing normal resting conditions, and the term steady state is often applied to exercise when there's a physiological variable that is constant, but that it may not equal the normal homeostatic resting variable. So there's literally hundreds of different control systems in the body, and the overall goal of most of them is to regulate some physiological variable at or near a constant value. So whether it's blood pressure, heart rate, breathing rate, temperature, blood sugar levels, hormone levels in the body, there's going to be loads of control systems that are in places, checks and balances that are there to make sure that those variables are regulated. At a cellular level, Control systems regulate activities such as protein breakdown and synthesis, energy production, and the maintenance of the appropriate amounts of stored nutrients. Almost every organ system in the body helps to work to maintain homeostasis. For example, the lungs, which are part of your pulmonary system, and the heart, which are part of your circulatory system, work together to replenish oxygen and to remove carbon dioxide from the body. How are all of these things controlled? Well, we'll start off by using a simple analogy, the home heating system. So here we've got an image of a Nest thermostat that you may have in your house. I don't. You might have a slightly more old-fashioned looking thermostat than that. But the principle of how it operates is the same. We set the temperature to whatever we want. In this case, it's set there on the thermostat to 20 degrees. Any variation in the temperature from this set point results in the control center initiating a response. So if the temperature rises above the set point in the room, it's detected by the thermostat, which signals the control center to turn off the heating, and the room will gradually cool down. If the temperature is too low, the opposite will occur, and the heating will turn on to raise the temperature. In both cases, the response of the control center was to correct the condition. In this case, we're talking about room temperature, and return us to the set point. So if it went too high, we turn off the heating. If it went too low, we turn on the heating. And the desired outcome is to maintain a nearly constant temperature in the room. So similar to that example, we have loads of control systems in our body, biological control systems, which are a series of interconnected components that maintain some chemical or physical parameter in the body at a near constant value. That's what they want to do. Biological control systems are composed of three elements. We have a sensor, which we see here in the kind of greeny blue colour. We have a control center, which we see in the yellowy colour there, and we have an effector in blue here. A sensor or a receptor is usually something that's located in the periphery of the body, or that's going to detect a change. Control center is usually the brain, and the effector is usually an organ that's going to affect the change. So what happens is that the sensor a signal will start in the body. That's going to begin the operation of this biological control system. The stimulus represents a change in the internal environment. So there's either too much or too little of something that the body wants to regulate. The stimulus excites or stimulates a receptor or a sensor in the body that is capable of detecting the change in the variable in question. So we've got loads of different types of sensors or receptors in the body. Some of them are located in your muscles and your tendons that detect the length of the muscle and give us information about our body position in space around us. There are sensors that are going to detect glucose levels. There's sensors that are going to detect temperature. There's sensors that are going to detect blood pressure, heart rate, all these different things, loads of different sensors that are going to pick up signals that let the body know whether something is too high or too low. When the receptor is triggered, it will send a message to the control center. That's usually your brain. The control center will then integrate the signal and send a message out to the effector. So it'll receive the signal, it'll decide on a course of action and send a signal back out to your effector. As we said, the effector is usually an organ in the body. So if we detect that we are too cold, your brain will send a signal to your muscles to start shivering, and that shivering, that involuntary contraction of your muscle, starts to generate a little bit of heat to try and warm us up. Once the internal environment returns to normal, or everything is back to its set point, if you warm up enough in that example we just gave a second ago, then there's going to be a decrease in the original stimulus. So whatever was triggering that sensor or receptor will be diminished. Therefore, the signal going to the brain will be diminished, and the signal that's been sent to the organ will be diminished, and the loop will be closed off. So this type of feedback is called a negative feedback loop, and it's the primary method responsible for maintaining homeostasis in the body. It's called a negative feedback loop because we are something is activated and then something is shut off in response. So once it comes back down, it gets shut off again. A good example of this negative feedback loop is the respiratory system's regulation of carbon dioxide in your extracellular fluid. So if there's an increase in carbon dioxide in your extracellular fluid, that's going to trigger a receptor which sends information to the respiratory control center in the brain, which results in our breathing rate to increase, and we're going to bring more air in and out of the lungs. So the effectors in this case are the respiratory muscles, which act to increase the breathing rate. The increase in breathing will help to reduce the extracellular carbon dioxide concentrations and bring them back to normal, thus re-establishing homeostasis. And then the signals that were triggering that whole event will be shut off and breathing will return to normal. Negative feedback loops, as I said, are the more common examples that we find in the body, but there are some examples of positive feedback loops that we see in the body, but they are much less common. The classic example of a positive feedback mechanism that you'll see in the textbooks is the enhancement of labour contractions as a woman is giving birth. So what happens is when the baby is ready to be delivered, the head of the baby moves into the birth canal and places pressure on the cervix, which stimulates sensory receptors in the cervix. These excited sensors will then send neural signals to the brain, which is the control center, which responds by triggering the release of certain hormones from the pituitary gland. That's the effector gland in this case. The hormone, specifically oxytocin, travels via the blood to the uterus and it promotes increased contractions. So the contractions get stronger and more frequent. As labour continues, the cervix becomes more stimulated and the uterine contractions become even stronger again. So we have a signal that is causing an increased reaction. That increased reaction is causing an increased signal, which causes an increased reaction, which causes an increased signal. So it's a positive feedback loop. It's getting stronger and stronger and stronger as it goes on, as opposed to a negative feedback loop, which is looking to correct something and shut it down. Once the baby is born, then the stimulus stops. There's no more pressure on the cervix, and the signal to release the oxytocin is removed. So therefore, labour is finished, labour stops, and the positive feedback mechanism is shut off. Now, positive feedback loops can be dangerous because they can result in runaway or damaging processes. So another example of this is the maintenance of blood pressure. Okay, so one of the ways that we regulate blood pressure is by managing the diameter of our blood vessels. So our blood vessels have the ability to dilate, to get bigger, or to contract, get smaller. If they dilate and get bigger, our blood pressure will decrease. If they contract and get smaller, our blood pressure will increase. It's like trying to, if you have a hose that is wide and a hose that is narrow, the narrow hose will have greater pressure in it and the water will be shooting out because of that greater pressure. One of the other ways we maintain our blood pressure is by regulating our heart rate. So increasing our heart rate and causing the heart to contract more strongly will result in a higher blood pressure. Your heart is pumping more quickly, driving more blood into the system. Every beat is a little bit stronger, so it's forcing more blood in. That also drives up your blood pressure. Now imagine that you have been involved in an accident, or someone has been involved in an accident and they are losing blood due to that trauma. So they have damaged an artery or a vein and they are losing blood out of the body. The body will sense that it's losing, it won't sense that it's losing blood. It will sense that its blood pressure is dropping because the pressure is, the vascular system is no longer a closed system. Blood is leaking out and the pressure will no longer be maintained. So that will send a signal to the brain that we need to up our blood pressure. Blood pressure is getting critically low. Hey, we better respond by increasing our blood pressure. So two of the things it can do are to cause the blood vessels to vasodilate, to open up, and cause the heart to beat faster and more forcibly to try and drive up the blood pressure. However, if you think about it logically, If you have that trauma, you've damaged a big artery in your body and you're losing blood, and your body responds by telling the arteries to open up further to increase blood flow and for your heart to beat faster, the outcome is that you will bleed out more quickly. You will lose blood at an even faster rate. So that is an example of a dangerous positive feedback loop, or a dangerous consequence of a positive feedback loop. So they are not so common in the body. We don't see them too often. And it is more common that you will see a negative feedback loop in the body. So let's keep that going. We'll give another example there. We'll talk about body temperature. So the human body is homeothermic. That means that it likes to maintain a normal core temperature of around about 37 degrees. For thermoregulatory purposes, the body can be regarded as having an inner core. So that's where the inside of our body, where we like to have temperature of around about 37 degrees, and then an outer shell that surrounds that core, where the ideal average temperature is a little bit lower, about 33 degrees, although this is very dependent on the environmental factors and the clothing that a person is wearing. Okay, so that can be in the outside environment, and the clothes that you're wearing can affect your outer core, not your outer core temperature, the temperature of the shell of your body, but always you'll be striving to maintain an inner core temperature of 37 degrees. So a person may be hypothermic or hyperthermic. Hypo, we mentioned it previously, is the prefix meaning under. So examples are hypodermic. A hypodermic needle is a needle that delivers something under the skin. Hypotension, low blood pressure. And in this case, hypothermia, low body temperature. Conversely, we have hyper. That's the prefix that means over or high. So we have hyperventilation, which is rapid breathing. We have hypertrophy, which is excessive growth of something in the body. And in this case, hyperthermia, where we have high body temperature. So let's go back and just recap briefly. We said there were 3 elements in a biological control system. We have a sensor, a control center, and an effector. For temperature regulation, there's thermal receptors located throughout the body which sense changes in body temperature. The control center is the brain, specifically it's your hypothalamus, and there's various effectors around the body that result in sweating or vasodilation and other outcomes that will help to lower body temperature or drive it up. When the sensors detect a change in your body temperature, the hypothalamus, that part in your brain, the control center, will coordinate the response to return the body to normal temperature. So if we're too hot, if we are hyperthermic, if our body is getting too warm, we're going to start sweating. Our body will detect that we are too hot, and the hypothalamus will then stimulate the blood vessels to dilate, and it'll divert blood flow to the skin. So more of your blood flow around your body will be shunted towards the skin, towards the surface of the body. Heat is, your blood is warm. It's a way of transferring heat around the body. So if we use the blood to transfer heat from the core of the body to the surface of the body, we can then lose that heat out of the body and help to cool us down. We also start to sweat, and that is when we release water onto the surface of our skin, and that helps to increase the rate that we lose heat out of the body depending on the environmental conditions. On the other side, then, if we sense that we are too cold, say we're hypothermic, our hypothalamus will send a different signal to result in it, which results in a different outcome. We'll start our muscles to involuntarily contract, and we will start shivering, and that involuntary contraction will start to generate heat, the same way that we would generate heat if we were exercising. And that heat is the body's endeavouring to raise the body temperature so that we are no longer cold. Once the body temperature returns to normal, so if we sweat and we lose a bit of heat, or if we warm up from shivering and we return to normal, the signals that were being sent from the control center, from the hypothalamus to the muscles or to the blood flow to the skin will be shut off, and things will return back down to normal. We're going to look at thermoregulation in a bit of more detail a little bit later in this module. So exercise specifically presents a very, very dramatic test of the body's homeostatic control systems, because exercise has the potential to disrupt so many homeostatic variables. For example, if we're exercising hard, skeletal muscle is going to produce a large amount of heat, which poses a challenge to the body to prevent overheating. Additionally, there's going to be increases in the amount of oxygen requirements in the muscle. There's going to be large amounts of carbon dioxide that is going to be produced. So these changes must be counteracted by increases in breathing and blood flow to increase oxygen delivery and CO2 removal. If we're talking really strictly, the body very rarely maintains true homeostasis when we're exercising, particularly if it's for a prolonged period of time, or if we're in a hot environment. Heavy exercise or prolonged work will result in disturbances to the internal environment that are generally too great for our bodily systems to overcome, and therefore steady state may not be possible during very heavy exercise or during extreme environments. An example of this here is the girl that you see in the picture there. That is Elisa Vainio, who is an athlete from Finland who was competing in the marathon in Doha in 2019, the Athletics World Championships. This was a controversial event because it was held in Doha, which is one of the hottest countries on earth. They took some extreme measures to try and control the environmental conditions, like putting air conditioning in the stadiums. And for the marathon specifically, the marathon start time was scheduled for midnight, because they hoped that would be the coolest part of the day. So it was known as the Midnight Marathon, kicked off in the middle of the night, in an attempt to try and offset the challenges that were going to be presented by the environmental conditions. Now, it turns out that they weren't so lucky. On the day that the marathon was run at midnight, I can't remember off the top of my head, but I think it was still like 34, 35 degrees at midnight, and it was very, very humid. So that placed significant challenges on the athletes. And in this series of images here of Elisa, it started out actually with this picture of her in the wheelchair, because she was one of a large number of athletes who started the marathon. Now remember, we're talking about elite athletes here competing at the Athletics World Championships, who started the marathon but were unable to complete the race. I think I'm right in saying that 60% of people who started the race dropped out because the conditions were so tough. We see her there in the previous pictures where she is desperately trying to maintain her core temperature. So she is not she's running in the heat at night, as we can see here. She's got a water bottle in each hand, one that she's pouring over her head and one that she's drinking from. So she's trying to get more to wet the surface of her skin to increase the rate of conductive heat loss. She's trying to get fluids on board because she's going to be sweating so profusely. She needs to maintain her hydration levels. Here she's still drinking, and she's got a sponge this time to try and get would have probably come from an ice bucket, to try and get ice cold water onto her body to maintain her ability to perform. But as we can see in the last picture here, she was unable to maintain her performance, and she had to drop out of the race due to the extreme challenge that the heat or exercising in the heat placed on her body, and she was unable to persist. However, our body can adapt. So one of the things that we try to get our body to do through exercise and training is to adapt and get better. The term adaptation refers to the change in the structure and function of a cell or an organ that results in an improved ability to maintain homeostasis during stressful conditions, or we might say to maintain a new steady state during stressful conditions. The body cell's ability to respond to a challenge is not fixed, and it can be improved by prolonged exposure to specific stresses. So if, for example, training, regular bouts of exercise, our body will adapt and get a little bit fitter, a little bit stronger. We can adapt to the heat or the cold through heat or cold exposure. You can acclimatize to a certain amount of heat. You can, and that's one of the key objectives of what we're going to do in this module. Over the course of the module, we're going to focus on how exercise disturbs homeostasis of the body during both acute exercise, and we'll consider how chronic adaptations occur following exercise training. Okay, that's where I want to park that today. We're going to follow up in the next lecture doing a recap on the cardiovascular system. So join me for that soon.